So this video is on posterior distributions with binomial experiments. So before we start, let's start by defining what a binomial distribution is, or a binomial experiment is. A binomial experiment is one where we have m independent trials and at each trial we either have a success. By all means, when we say success, we imply an event of interest. Or a failure. And we know the probability of success. And that would be P, which naturally would imply that the probability of failure is 1 minus P. So let us consider a simple binomial experiment. So we'll have an example here. I don't want to do 10, let's just do 5. We are selecting 5 individuals at random. And the probability that an individual likes tacos is 0.712. And let's say X is the number of individuals out of the 5 individuals who like tacos. And let's say, you know, what the distribution is. So find the probability x is equal to lowercase x. Now, x is the number of individuals out of the 5 individuals who like tacos. So the possible values for x are 0, 1, 2, 3, 4, and 5. So, in other words, none of the 5 individuals like tacos, exactly 1 of them likes tacos, exactly 2 out of those 5 like tacos, exactly 3 out of 5 like tacos, and so forth. Now, what is the general formula? The formula here for the distribution is m choose x times p raised x times 1 minus m minus x. Here we have m to be equal to 5, and the probability that a person likes tacos would be the probability of success, because our event of interest is a person liking tacos. So the probability of success is 0.712. So let's see if we can come up with the distribution. So the possible values for x are 0, 1, 2, 3, 4, and 5. And you can plug in the formula to find the probabilities, but I'm going to show you how to find these probabilities using the calculator. So if we press second march on the TR-84 and scroll down, we have Binomial PDF. We plug in M and the probability of success and X. We start with 0. And that probability is 0.002. Let's find the probability of 1. And that is 0.0245. The probability of 2. That is 0.1211. The probability of 3. Point 2933, the probability of 4, 0.37, and the probability of 5. We'll call it 183. So what we have here is a discrete distribution, and if we add all the probabilities, it is going to sum to 1. So we have the distribution here, and based on this, we could see that it is more likely that the number of individuals out of the 5 individuals who would like tacos would be, kind of between 2 and 5. And the most likely possibility here would be 4, because that probability is 0.37. So now that we have this information, let's say someone asks you this question. So we go around and collect or observe 10 different groups of 5 people each, and we would like to know the number of people out of the 5 individuals in a group who like tacos, and this is the information we collected. And the sample, in the first group there were 3 people, second there were 4, third there were 4, fourth 2, fifth 4, 1, 4, 3, 5, and 1. So those are the 10 groups, and this is what I've found. So the question here, mind you, I'm creating this sample with that distribution in mind, the one we just found. And the most likely one is 4, and the other values 2, 3, 4, and 5 are also possible, but not with the same frequency. So we want to know what is the most likely probability of success. To remain consistent, I will just call that parameter P as theta. So theta is the probability of success. And let me add, is it 0.6 or 0.2? So those are the two possibilities. So in order to find this, we're going to compute the likelihood. Which is simply the probability that we observe the sample X given the parameter theta. So that is the sample of 10 values in the question and the parameter theta. And that is proportional to the product of I equals 1 to 10, the probability of seeing each of the observations, that is just multiplication rule. So we would have probability of X given theta to be equal to the product of I equals 1 to 10, M choose Xi times theta raise Xi, 1 minus theta raise M minus Xi. Now, for reasons that I cannot go over here, I will simply say that likelihood is proportional to the product I equals 1 to 10 theta raise Xi times 1 minus theta raise M minus Xi. So that would be proportional to, I am going to multiply that term to itself 10 times. That's what the product means. So this would become theta raise sum I equals 1 to 10 Xi. The reason being you have theta raise x1 times theta raise x2 all the way up to theta raise x10. The bases are identical, so if I add everything, I have x1 plus x2 all the way up to x10, which is simply that sum right there. In a similar manner, I would have 1 minus theta raise. I'm going to sum m minus xi 10 times. Which would give us theta raise sum I equals 1 to 10 xi, 1 minus theta. If I add m to itself 10 times, I would get 10 times m minus sum I equals 1 to 10 xi. So that is the likelihood function. As you can see, this formula that we have, the above likelihood function, is for a sample of size n equals 10. So if I want to generalize it for any sample, the 10 would get replaced by the sample size. So for a sample of size n, the likelihood function in a binomial experiment with m independent trials and probability of success theta is probability x given theta multiplied, so it's proportional to theta raised n or sum I equals 1 to n xi times 1 minus theta m times n minus sum I equals 1 to n xi. But we know the average of a sample x bar is equal to sum I equals 1 to n xi divided by n. This would mean if I rewrite it, I'll have the sum I equals 1 to n xi equals n times x bar. So we could also write the likelihood function as the probability x given theta proportional to theta raised n minus, x bar times n, 1 minus theta m times n minus n times x bar, which is simply theta raised nx bar 1 minus theta n times m minus x bar. So that is the likelihood function for a sample of size n. Let's go back to our example where n is simply 10. And we actually have the sample, which is from 10 groups, and we have 3, 4, 4, 2, 4, 1, 5, 3, 5, 1. Each group has 5 individuals, and we asked them, and 3 out of 5 said they like tacos. The next one gave, 4 out of 5, and so forth. The question here is which is more likely, 0.6 or 0.2 for the probability of success. So we are going to make use of the likelihood function. So as I mentioned earlier, I created the sample using the distribution that's right here. So I know the truth about that distribution. Its probability of success is 0.712. So if I were a betting individual, I am going to lean toward 0.6. So let's see if we get that answer with the likelihood function. So first, we ask the question, is theta equals 0.6? So the probability of seeing the sample that we have so the sample of 10 values should be proportional to 0.6, the value of theta in this formula, and 1 minus 0.6, and the powers, 10 times the mean, and 10 times m is 5 because we have 5 individuals per group minus the mean x bar. So let's see what the mean of the sample is. So let's enter the sample in the calculator. Three, 4, 4, 2, 4, 1, 4, 3, 5, and 1. Second mode to exit. And I'm going to do one variable statistics of the data in list 1. I end up guessing the mean to be 3.1. That is the sample mean. Now, of course, we can't have 3.1 individuals, so we typically round to the nearest integer, but I'm not going to do that here because I'm focused on the likelihood, so I'm simply going to write it as 0.6 raise 10 times 3.1 and 0.4, 1 minus 0.6 is 0.4, 10 times 5 minus 3.1, which is 0.6 raise 31 times 0.4 raise 5 minus 3.1, which is 1.9, so we'll just put it as 19. So let's evaluate this. This value is going to be proportional to 0.6 raised 31 times 0.4 raised 19. And that seems to be a significantly large number, small number. You know, we have 10 raised negative 15. So oftentimes we like to put this in the log scale. So in the log scale, that would give us the log likelihood. So I'm converting the likelihood to log likelihood, and that value would be proportional to the log. We typically go for natural logarithm, so natural logarithm of based on logarithm, so trying to find it, log 3.4646 times 10 raised negative 5 or negative 15. We're just doing this so that we can look at things easily, numerically. In terms of understanding, this is easier to interpret compared to that. So if you can do it with extremely small values, you could go ahead and do it. There is nothing wrong with that. So when theta is 0.6, we ended up getting negative 14.43 as the log likelihood. Now the next question is theta equal to 0.2. We are going to do the same process. What are the chances of observing the sample that we have given theta is 0.2? And that is going to be proportional to theta raised to the power n minus x bar, n times x bar, which is 10 times the mean, and we found the mean to be 3.1, and 1 minus 0.2 raised 10 times 5 minus 3.1. And that gives us 0.2 raised 31 times 0.8 raised 19. And that ends up being 3.094 times 10 raised negative 24 in the log scale. We end up having negative 23.509. So, which is more likely? So, we want to look at the maximum of these two possibilities. Clearly, negative 14.43 is bigger than negative 23.509, so theta is equal to 0.6. Remember, when I first started the problem, I said I am formulating this sample using that particular distribution, and that particular distribution had a success probability of 0.712, and I said out of these two possibilities, 0.6 or 0.2, the answer is more likely to be 0.6, and that is exactly what we got. And mind you, here we're simply looking at the likelihood function. There is no prior information involved, so we are going to come up with a Bayesian approach here. So suppose the prior for theta is probability of theta, and we know the likelihood is probability of the sample x given theta is proportional to theta raised n times x bar 1 minus theta times n times m minus x bar. This would mean the posterior distribution is proportional to the probability of theta given x, which is the probability of x given theta times the probability of theta. We're using proportional sign here to keep things simple again. So anytime we have a binomial experiment, the conjugate prior of a binomial distribution, you know where I'm going with this, is a beta distribution with parameters A and B. So if we plug that here in our regular expression, which is that would give us the posterior distribution, we will have the probability of theta given x proportional to the likelihood theta raised n minus x bar 1 minus theta raised n times m minus x bar multiplied by a regular beta distribution, which is theta raised a minus 1 and 1 minus theta raised b minus 1. So the posterior distribution is probability of theta given x proportional to theta. So I'm going to combine those two terms. And I'm going to combine that term with that term. Bases are identical, combine the powers, n times m minus x bar plus b minus 1. And that looks like another beta distribution. So that would be our new A, and that is our new B. So the posterior in this case is simply beta n x bar plus A, comma, n times m minus x bar plus b. And we always know that the posterior mean here is simply A over A plus B. The new value of A, I'll call it A post, and B post. We have A post over A plus or A post plus B post, which is n x bar plus the A of the prior divided by n x bar plus A of the prior plus n times m minus x bar plus b of the prior. So we would have n x bar plus A divided by n x bar plus A plus mn minus n x bar plus b. Those two terms would go away, so the final expression for the mean is n x bar plus A divided by A plus mn plus b. So in a similar manner, we could use the variance of a beta distribution and come up with the variance of the posterior distribution. So the standard formula would give us A post times B post divided by A post plus B post squared times A post plus B post minus 1. We have the value of A post, which is n x bar plus A. We multiply it by B post, which is n times m minus x bar plus b, divided by, we know the value of A post plus B post. A post plus B post simply reduces to A plus mn plus B squared. And use the same argument here. We have A plus mn plus B minus 1. So that would be the variance. So we have the mean and we have the variance. Now, if we plug in m to be equal to 1, we would get the expressions for the binomial experiment. So now we have the posterior mean and the posterior variance and the posterior distribution. So let's go back to the previous problem that we were looking at. Suppose the prior for theta, which is the probability that someone likes tacos, is beta 1, 2. And now we want to ask the question, is the value of theta 0.6 or is it 0.2? So we are going to see how the prior information is going to affect our conclusion. Now, as you know, that is the fundamental reason for using Bayesian statistics. So how do we find that? We know, we just derived that the posterior of theta, given the data or the evidence, which is x, that in the example has 10 observations, is simply that expression, which is beta distribution with n x bar plus a, comma, n times m minus x bar plus b. So we simply plug in the values. We know x bar is 3.1. The number of observations we have is 10. The prior value for A is 1. The prior value for B is 2. And the number of individuals per group is 5. So that would mean the posterior of theta is simply beta 10 times 3.1 plus 1, 10 times 5 minus 3.1 plus 2. So that would indicate beta is 32, 21. So how do we find the probability here? We know that the density here is beta, and we know beta is proportional to theta raised a minus 1 and 1 minus theta raised b minus 1. So, which would mean theta, the new value of a in the posterior, is 32 minus 1 and 1 minus theta raised 21 minus 1. So, which is the most likely value? Let us plug in 0.6 given the data or the evidence, which is 0.6 raised 31 times 1 minus 0.6 raised 19. Oh, sorry, bad math there. 20. And that would give us 0.6 raised 31 times 0.4 raised 20. We get 1.45 times 10 raised negative 15. And if we put it in log scale, we get the value, the log probability of the posterior. It's negative 14.83. And we'll do the same thing with 0.2. would be proportional to 0.2 raised 32 minus 1, 1 minus 0.2 raised 21 minus 1. So 0.2 raised 31 times 0.8 raised 20. That gives us 2.47 times 10 raised negative 4, and in the log scale, log of probability of theta equals 0.2, given x is the log of the answer. And that is negative 23.61. Clearly, negative 4.83 is a bigger number than negative 23.61, so the value of theta is once again 0.6. And if we go back and look at the likelihood, which is right here, we have negative 14.43 and negative 23.509, and the new values we got, they are pretty close to what we have. So what is our conclusion? The conclusion here is that the prior didn't have a significant effect on the posterior. Now we could extend this to asking one more question. So assuming a normal approximation, what is the probability that theta is greater? So we're going to do theta post is greater than 0.8. Now, even before we start, we are going to expect to have this probability to be a smaller value, because it seems like the most likely value is about 0.6. So let's see if we can find this value. Since we're using a normal approximation, we would want to know the posterior mean, which is A post divided by A post plus B post, which is simply 32 divided by 32 plus 20. Which is 0.6154. And the variance is A post times B post divided by A post plus B post squared multiplied by A post plus B post minus 1. I feel like I made a mistake here. This should be plus 1, so let's go ahead and change that in the variance here. That is plus 1, plus 1. So the value now becomes 32 times 20 divided by 52 squared times 53. So 32 times 20 divided by 52 squared times 53. That happens to be 0.0044. Or 45. So that is the variance, which would imply the standard deviation is the square root of 0.0045. Which is 0.210, or simply write it as 211. So that is the standard deviation. So let's say we're using a normal approximation. So we'd like to know the probability that theta is going to be greater than 0.8. So we could use normal CDF because we are doing a normal approximation. 0.8, the mean is 0.6, the standard deviation is 0.211. It's not 0.6, it's actually 0.6154. So start. Not start, second vars, 0.8, 0.6154, comma, 0.211. And that, I forgot to put the infinity part. So 0.8, I'm doing R stuff here. Forgot that I'm using a calculator. So 0.8 E99 0.6154, comma 0.211. So 0.8 E99, comma 0.6154, comma 0.211. And there is only about a 19% chance that the value of theta is going to be greater than 0.8. In a similar manner, what are the chances theta is less than 0.2? Now, it should have come to your mind already that this is going to be a very small value, because we know that theta is more likely to be 0.6 and not 0.2. So using the posterior distribution, probability of theta less than 0.2 is simply normal CDF, negative E99, 0.2, 0.6154, and 0.211. And it is a small value, and it's only about a 2% or 2.5% chance that the value of theta, in other words, the probability that an individual would like tacos, out of 5 individuals, or the probability that an individual would like tacos is simply 0.0245 or 2.5%.